Hey everyone, welcome back to Spatial Stats. So last time we finished, I think right around this slide, where I used an isotropic and the anisotropic model. Those are kind of tough to say. The isotropic and the anisotropic model to predict precipitation in the state of Colorado. And I stopped here because I'm showing that there's a pretty minimal difference between the predictions between anisotropic and isotropic models. If you recall, with anisotropy, we estimate two additional parameters. One is the angle theta. And in this case, our angle was about 155 degrees, counterclockwise rotation. So roughly in that direction. And then we also estimate how much larger spatial correlation is in that direction by compressing distances, inducing a compression of distances of our observed locations. So my anisotropy ratio lambda, the ratio of major to minor axis, was about 1.5. So around the state of Colorado, we're saying that in machine learning terms, we're learning about 1.5 times more from data along the angle of 155 degrees. And actually, if you look really closely, our prediction standard deviations are very much ellipses, whereas in the isotropic world, these are definitely circles. And of course, how large our ellipses are and how large our circles are is determined by the range. So today, I wanted to dive deeper into how prediction is performed, because after all, that is one of the two major goals of modeling with geostatistical data. The first is to estimate coefficients and their correct standard errors. And this is the spatial information enters through those GLS equations that we saw when we were doing our maximum likelihood by hand example. We very much now want to use our model to make predictions where we have not had data. We don't have weather stations everywhere. We'll only have 195, it's actually quite a bit of weather stations, but we want to predict weather everywhere. So we use our model to make predictions. Literature delineates between three different kinds of prediction. So the first is called simple Kriging. It basically assumes that you have a known mean. That is just never realistic. In the statistics world, assuming that you have a known mean, I never want to do that. So simple Kriging is just not a realistic set of circumstances. So between these two, the difference is ordinary Kriging has a constant unknown mean. So we're dealing with only the intercept. And universal Kriging has a spatially varying unknown mean. So we have several covariates in that mean function, like we just did with the Colorado example, because we had the intercept, the elevation, east-west slope, and the interaction between elevation and east-west slope. What does the interaction pick up? High peaks that are slanted in one direction versus the other. So which one we pick very much depends on what happens where we don't have data. Do we have covariates where we want to make predictions, or do we not have covariates where we want to make predictions? If we are in a world where we don't have covariates where we want to make predictions, we specify a constant unknown mean and let the spatial effect take care of the peaks and the valleys of the outcome variable. But if we do have reliable measurements where we want to make predictions, we want to incorporate them into the prediction equation, then we rely on the universal Kriging. So in the next couple of slides, I will focus on the case with universal Kriging because it is the only difference between it and ordinary Kriging is where universal Kriging is a special case where we only have the intercept. So everything I say will apply to both, generally speaking. And so we can take a look if we denote S0, S naught, as our new location and Y at S0 as our predicted value at an unobserved location, then here is the distribution of data at our new location or set of new locations. Shouldn't surprise us, it's a normal distribution. We've been assuming multivariate normality thus far. And so that it makes sense at our unobserved location, data will also be distributed according to a normal distribution or multivariate normal. So there's a number of components to look at. So we're going to look at them one at a time. There is my mean function. So my covariates at the new location contributing and evaluating with the mean function. With ordinary Kriging, this would just be the intercept. If you have covariates, you just perform that matrix multiplication and make your mean function at your unobserved location. Okay, easy enough. The next bit I want to point out are the model residuals. So our prediction at a new location is a sum of the mean there and some function of all the residuals. The mean predicted at our new location plus some function of the residuals. What do I mean by some function? It is a weighted average of all of the modeled residuals. So we're going to take a look and dig in to these, what are called spatial weights. These two terms multiplied together are called spatial weights that tell us how much the different residuals are going to influence the mean prediction at our new location. So gamma specifically is the distance between all of our observed locations and the new location fed into our spatial correlation function. It's basically a scaled correlation between all of our observed data and wherever we want to make a prediction. We find our distances, feed them into our correlation function. Here is the range parameter. Here is the partial CIL. And so we make our scaled correlation. This is, of course, the inverse variance covariance matrix that itself contains spatial information. All right, moving on to uncertainty. Here is the total variance, alpha squared and tau squared is the total variance. And notice that we actually reduce the total variance. So we reduce uncertainty by this quadratic form. Anything in this format where you have a vector prime vector is called a quadratic form. So we reduce the uncertainty of this prediction by the magnitude of correlations between all of our observed data and the new unobserved location. So let's dig in, spend some time digging into these spatial weights. So I'm going to use a toy example. It will have 5 locations. They're just numbered 1 through 5 on the screen. I'm going to specify a constant mean of 1 for my toy example, so more like ordinary Kriging. I will specify no nugget and a spatial variance of 2, right? So we're keeping track. Alpha squared is 2, tau squared is 0, and an exponential correlation function. That's our rho. So up here, this spatial correlation function, I'm assuming, is an exponential. Okay. Come on. So I have data from 0, 0 to 2, 2, and everything in between. Here is, of course, I laid out these 5 points very deliberately. What is my maximum observed distance in these data? Well, it's between 0, 0 and 2, 2, and also between 0, 2 and 2, 0. So the length of those diagonals find my Euclidean matrix distance, excuse me. 2 minus 0 squared plus 2 minus 0 squared is square root of 8, which is approximately, I believe, 2.3-ish. Meanwhile, with a phi of 0.5 and an exponential correlation function, my effective range is 3 over 0.5. And so my effective range is 6. So basically all points are correlated by design. My effective range is 6. My maximum observed distance is 2.3. Clearly, all of my data are spatially correlated. I'm going to put in my toy example, I want to make a prediction. Struggling with this presentation right now. Hopefully this won't blue screen like it did on me last night, guys. Alrighty, I will just have to use the mouse because this is, it's really struggling right now, and I remember struggling with it before I got a blue screen of death last night. So I would love to use the stylus though. Okay, there we go. I would like to make a prediction at x, which is located at an x coordinate of 0 and a y coordinate of 1. So the first thing I'm going to look at are the elements of this gamma function, which is just the distances between our observed location and the location I want to predict, all pulled through the exponential correlation function. There's my exponential correlation function. There's my range parameter of 0.5, and we scale it by our spatial variance of 2. So my distance vectors, I have 2 possible values because 3 points, 1, 2, and 5, are equidistant from x. 2 of those points, 4 and 3, are a little bit farther away, a little more than twice as far. So here is my distance vector. It's the distance between all 5 of my observed locations and x. And I feed those distances through my exponential correlation function with a range parameter of 0.5 scaled by sigma squared, and I get this. So do these elements make sense? The bigger the element, the greater the influence. So yes, 1, 2, and 5 all have equal influence because they are closer to x. And 4 and 3 have smaller influence because they're farther away. Notice that the effective distance is not linear, and we shouldn't expect it to be linear, right? My spatial correlation function very much looks like this. So at some point, distance sort of stops to matter, but it matters a lot in the beginning. I'm just reciting the shape of the exponential correlation function. So these gamma terms, things that are farther away matter less, and things that are equidistant matter an equal amount. So far, so good. All right, now we're going to expand to the full term that I have highlighted there. It's not working, and I'm afraid of the blue screen of death. So I'm expanding my focus now to this whole term. The spatial weights are a combination of our gamma and our inverse variance covariance matrix. So what I have here are my observations. I have my distance vector that I've just described to you. And I can now finally get control of my stylus back. Here are my spatial weights. So you should see something kind of interesting. The spatial weights apply to the residuals. They actually describe how much each model residual will influence the prediction at X. Something interesting has occurred. Yes, 1, 2, and 5 have the greatest impact, as you would expect. But point number 5 has a smaller impact than either 2 or 1, although these 3 points are equidistant. So what is happening? What is going on? By the way, notice that 4 and 3, according to our spatial weights, the residuals at 4 and 3 almost don't matter at all. Those weights are really close to 0. But the interesting thing that we show here is that 1 and 2 have equal weights, but 5 has a smaller weight. Why is that? Well, the answer lies in the correlation matrix among all 5 observed data points. You guys are no strangers to a correlation matrix. One's in the main diagonal. Off diagonals have the correlations between the 5 locations. So what point shares the most information with the other points? Why, it is absolutely point number 5. Point number 5 is most correlated with the other 4 points. So the information at number 5 is not as independent as elsewhere. So what these spatial weights do, we actually downweigh correlated points. And we assign a greater weight to what I like to think are these anchor points. 1 and 2 are farther apart. Information at 1 and 2 constitutes more so independent pieces of information that can contribute to making our prediction. Information at 5, because of the fact that 5 shares almost half of the information with all of the other points, thus gets downweighted and contributes a little bit less, although the distances are identical. So all of that is the contribution of multiplying by our sigma inverse. It's just going to be a struggle today, guys. Let's take a closer look to that sigma inverse. So I'm running the sigma inverse for a few different values of phi. So a value of phi of 0.1, a value of phi of 0.5, that's how data were generated, and a value of phi of 2.5. By the way, value of phi of 0.1, right? Phi equals 0.1. The effective range is 30. Remember, my greatest observed distance is like square root of 8. So I'm saying everything is super correlated. 0.5, my effective range is 6. Everything is still fairly correlated. Notice there's very little change in these spatial weights. This goes along with the theme that the range parameter has sort of a nebulous effect. It does have an effect, right? Because when phi is effective range of phi of 2.5, 3 over 2.5, you know, it's, I don't know, 1.4, 1.5-ish. Data are almost uncorrelated, when phi is 2.5. There's not a ton of spatial information when phi is 2.5. And accordingly, the spatial weights, how much the residuals at all of our observed locations influence the new prediction, are all very close to 0. But I'm just gonna, there it is. Notice this is a 5-fold difference in phi, and this too is a 5-fold difference in phi. But the spatial weights here hardly move, whereas the spatial weights here change quite a bit. So it's really hard to intuit the effect of phi after we get a certain degree correlated, right? Effective range of 6, effective range of 30, but the effect on the spatial weights is very, very minimal. So phi has kind of a strange impact. Moving on to our uncertainty. We take the total variance, we reduce it by this quadratic form. So what I did was I plotted the value of that quadratic form, so just the gamma prime sigma inverse gamma, as a function of the effective range. So this is by how much we reduce. This is by how much we reduce our uncertainty. So when the effective range is near 0, data are almost independent. So our best guess is uninfluenced by other observations. So our uncertainty is reduced by near 0. As our effective range grows, well, first of all, it's a nonlinear impact, right? The reduction in uncertainty is profound up until an effective range of 10, and then quite flat past 10. Maximum observed distance is 2.3. And look, we are approaching 2. Even when our data are correlated to a completely ridiculous degree, we still can't reduce our effective range. Reduce our uncertainty by more than 2. Remember that this gamma term is scaled by the spatial variance as well. So intuitively, the largest that uncertainty in our prediction can be is the total variance, which in this case is 2. How does this uncertainty change? Well, a lot at first. And then almost not at all after about an effective range of 10. So what I've noticed in my experience, if data are either all really, really correlated and you get this crazy large effective range, or data are uncorrelated, the biggest impact that the spatial model has is if you fall somewhere in the middle. If your data are somewhere like moderately correlated, is when you have the biggest observed effect on uncertainty. Among 5 observations that are at most, say, 2.3 units apart, I wouldn't believe an estimated effective range of 60 anyway. Something went wrong, something went off the rails. I wouldn't believe it anyway. Okay, so we're still trying to predict this point at x. If I plug in my numbers by incorporating the distances between x and all my observed values, by the fact that 5 doesn't count as a separate data point, 5 shares all of this information among all the data points, and finally weighting all of my residuals by these spatial weights, I get my predictive distribution at my observed location. So this right here is what the distribution of data at x is predicted to be. So, values between 0 and 1 are pretty typical, with a variance of 0.83. So it's pretty unlikely that that value will be above 3 or below -1, for example. So we get a full predictive distribution of data at our unobserved location. What happens if we move our new location? All right, I just moved my unobserved location right over here. Notice that I now get the same case. I have 3 equidistant points, one of which will matter less. What this means is that my quadratic term trying to show you that my quadratic term does not change. So my uncertainty doesn't change. But the mean does change because now I am more influenced by these 2 points than by any other points. So my predicted distribution is now centered at -1. That is on average my best guess about X, but my uncertainty doesn't change. I'm now 1 unit away from all these and 2.23 units away from these. Whoops. 2.23 units away from these. I think you know where this is going. We're now going to move our predicted point closer to an observed point. So my distance vectors now look completely different. And my spatial weights now have one that stands above the rest. And intuitively, it is number 5. It is point number 5 that has the greatest influence on our prediction. Number 4 has the second greatest influence. So really, these are fairly negligible. The prediction of X will be mostly between an average of these 2 points, and much more so number 5 than number 4. What I want you to pay attention to is because we have moved our prediction closer to an observed value, because we have moved our prediction closer to where I have an observed piece of data, I get to reduce my uncertainty. My variance is now 0.43, whereas on the previous slide, where my prediction was occurring equal farther away from where I have observations, I almost half my uncertainty. So because we are closer to an observation, we have less uncertainty. And that too should make a ton of intuitive sense. The closer we are to what we observed, the less uncertainty we need to propagate. And now, finally, I think maybe you can see and believe me what these prediction standard deviations look like, right? Each one of these ellipses or circles, ellipses on the top, circles on the bottom, has a little white dot in the middle. That's because we are at the location where we have a weather station. At the location where we have a weather station, we have minimal uncertainty. As we get farther away, we approach our maximal uncertainty, which is just defined by the total variance, which happens out here and out there. As we get farther away from weather stations, we should say we have more uncertainty in our data. Okay. Now, to close out this crazy unit, I want to take a look at model comparison. I have pretty quickly said, oh, let's take a look at the AIC, the BIC, but I want to treat it with a little bit more detail right now. So statistical models are evaluated usually using something like an R² for within sample fit. We want that proportion of variability to be as high as possible. And information criteria, and there are a ton, for out of sample or predicted fit. Most of the time in the literature, we favor information criteria because we always want to predict the next observation, the one that is not a part of our sample. It's interesting because the information criteria is essentially the distance between the truth and what our model thinks. And since we want to be closer to the truth, we pick a model with smaller information criteria and large R squared. Right? So information criteria, estimated distance between the true data generating process and what is assumed by the model. We want this to be as small as possible, intuitively. And so we prefer models with small information criteria and large R squared. By the way, the units of information criteria are meaningless. So whether you are comparing, something like 5,000,007, you're comparing 5,000,007 to 5,000,005, you're going to prefer a model with an information criteria of 5,000,005. 5,000,005 what? The units of meaningless. So we looked at that briefly in R last time, but all information criteria basically have a penalty term and the log likelihood. So we take our log likelihood and we assign a penalty. We add something, and remember, we prefer information criteria that is small. That's why when we add a penalty, it's a penalty. The penalty term prevents us from fitting too many parameters, from overfitting the data. So for example, GOR helpfully outputs the log likelihood for the isotropic model and the non-spatial model. So we want the log likelihood to be as large as possible. So clearly, between these two models, we'll prefer the spatial model, right? This is the spatial model. And this is the non-spatial model. The log likelihood of the spatial model is bigger. So just by that alone, which is an estimate of goodness of fit, we want that to be as large as possible. We will prefer the spatial model. But the spatial model does estimate 2 additional parameters, and it's always fun to try and count them, right? So this is from the Colorado data. So the non-spatial model has an intercept, main effective elevation, main effective slope, the interaction between elevation and slope, that makes 4. What's the 5th one? Residual standard deviation. I need 2 more to make it to my spatial isotropic spatial model. Well, the one additional one that an isotropic spatial model estimates is the range parameter that makes 6. And then which one is the other one? Well, in a spatial model, we partition that residual standard deviation into a spatial and a non-spatial component. So that's how we get 7 total parameters. The anisotropic model estimates 2 more parameters above the isotropic model, because now we estimate the anisotropic angle and the anisotropic ratio. But look, the log likelihood also increased. So if you were just looking at the log likelihood, which you shouldn't be, but if you were, you would prefer the one with the largest log likelihood, and you would prefer the anisotropic model. Probably the most used and the most misused information criteria is the AIC. That man on the slide is Hirotugu Akaike, who is responsible, of course, for the information criteria. It's one of the most cited papers of all time. That's a ranking as of last year. I have not looked it up. Feel free to correct me if you'd like. So the reason why, so it has a kind of a familiar form. We penalize our log likelihood by 2 times the total number of parameters. That's how we control for overfitting. It is misused because AIC correctly estimates the distance between the model and the truth. That's what the information criteria is trying to do, estimate the distance between the model and the truth, if the ratio of observations per parameter is large. That means we're estimating relatively few things for how many pieces of information we have. Notice in a spatial world, it's the complete opposite. We often estimate one unknown per observation, right? Think about the spatial effect. We have the mean function. We have as many spatial effects as we have observations. And we have the variance covariance parameters that estimate the correlation between the spatial effects. So any spatial analysis basically does not meet this criteria. And unfortunately, what they found was if the observations per parameter is small, AIC selects models that are too complex and tends to overfit. And I hear you asking, isn't that what it's designed to prevent? Hence the misuse, right? So AIC was invented in the 40s, where I think people couldn't imagine that we would have as much data and estimate as complex a model as we can just on our laptop computer. So the original AIC was designed to work where you have a lot of information per parameter. Otherwise, it is biased and it tends to select big models, complex models. So here I've incorporated the AIC in my output. Comparing AIC between the non-spatial model and the spatial model, distance between the model and the truth, well, smaller number is better. I will undoubtedly select the isotropic spatial model over the non-spatial model, but it gets more interesting when we compare the anisotropic model to the isotropic model. Yes, AIC of 5.5 is clearly less than an AIC of 6.4, but how different are they really? I'll leave that hanging for a minute. In 1989, which would have been about 40 years after the original AIC was reported, Hurwicz and Tsai came up with the corrected AIC. The corrected AIC incorporates n into the computation. The original AIC only depends on the log likelihood and how many parameters you have. Notice that as you get more and more data, n approaches infinity, you get this correction term. So look, this right here is the original AIC. And then we have this correction term. If I have something like 1 million over 1 million minus 1, this approaches 1. So as n approaches infinity, our correction term goes to 1, and our corrected AIC approaches the original AIC. How often are we working with 1 million observations? Well, it depends on who you ask. But it's the corrected AIC that correctly approximates the distance between the truth and the world assumed by the model. It corrects the issues, the overfitting issues that are inherent within their original AIC. However, I think the reason why it's not used as much, there is one R package that is, I think they could have named it a little better. It's the AICC mod average package, which I always forget how to spell. Remember, R is case sensitive. So for spatial models, I end up having to compute them by hand. And let me flip to R and show you how that's done. So I have two models. Here is my isotropic model and anisotropic model. These are from GeoR. So I'm just outputting the AIC here of the isotropic model and the AIC of the anisotropic model. The corrected AIC has -2 times the log likelihood. All right, here's -2 times the log likelihood. So let's see what this log likelihood actually produces. It reminds us that we estimated 7 parameters, and here is my log likelihood. The anisotropic model estimates 2 more parameters. Whoops. Yep, so it estimates 9 parameters, and there is my bigger log likelihood. So now I'm adding this term, right? Here is 2 times the number of parameters, 2 times the number of parameters. And here is my correction term. 195 is well, 195 is the number of observations that I have. It's the number of locations that I have. So this is my corrected AIC for the isotropic model, because I'm using the isotropic model's likelihood. And here is my corrected AIC for the anisotropic model. The anisotropic model still is a hair out in front, a hair out in front. Now, I want to talk about the elephant in the room. People have very strong opinions about the BIC, especially our friends in social sciences, I find, have very strong opinions about the BIC. A couple of things. It is not at all Bayesian. And sometimes it's called the SBIC because it's the Schwartz. It was Gideon Schwartz, I believe, who invented it in 1978. Sometimes it's called the SIC, just to confuse everybody. It is not Bayesian. It does, however, incorporate log n as into the penalty term. And for the life of me, I could not understand why does the penalty increase with n? Shouldn't the penalty decrease with n? You know, isn't it harder to overfit a large data set because we have a lot more information? So that never quite made sense to me. The other thing that didn't make sense to me is if you read exactly how what the BIC is designed to do, it says if, and that's a big if, the true model is among the set you are considering. If the ultimate truth is among the models that you are considering, it promises to select it as n approaches infinity. So 2 problems with that. I do not proclaim to know the ultimate truth. If you do, come talk to me. I want to learn things from you. I also have a problem with this n approaching infinity. No one has time for that, to collect that much data. No one has resources for that. So I think a few things about the BIC. It is widely used and some people swear by it. I think it has a couple of fundamental questions that I want to ask. I like the concept behind the corrected AIC a lot more. This distance between the model and the truth. So in my practice, in my science, in my statistical analysis, I will prefer the corrected AIC. By the way, if you do compare the BICs of our 2 models, well, they're going to tell you the opposite, right? So that's the curse of looking at too many ICs. You start to not have much information because you start to compare too many information criteria that start to conflict with one another, right? AIC barely selects the anisotropic model over the isotropic model. The corrected AIC agrees. The BIC says the isotropic BIC is smaller than the anisotropic BIC. So do with that as you will. Here is the last word that I have for you on model comparison. There's a lot of challenges. You know, how many should you look at? 1 information criteria or like 7? How do you break ties? What if your models are tied in? Suppose you look at 7 information criteria, and yes, there are probably more than 7 out there. Suppose your models are tied in 3 and not tied in 4. How do you decide? So there's something interesting that I found in one of the spatial books that I used to sort of help me prepare for a course. And this doesn't work. So you know what? I'm just going to put it down because we're in the last slide. The information criteria tends to group models into sets that are clearly inferior with similar values. So one should not necessarily adopt the model with the smallest information criteria, but a model in the group of plausible models that is both parsimonious and interpretable. So my take on Colorado. Treat the isotropic and the anisotropic model as being basically identical. And since the anisotropic model offers us a chance to learn more in one direction, go ahead and go with it. If they're identical and one model gives you additional information, go with that model. With that, this really long unit, but really fun unit, I enjoyed this quite a bit. I really hope you do too, is finished. Look out for our synchronous activity next Tuesday. Thank you guys for your attention. I hope you're well. I hope you're staying safe out there and have yourselves a great weekend. Bye-bye.